Hello back. Time to talk about what you can do synthetically with sugars. Once again, from the point of view of organic chemistry. The first one is conversions into esters and ethers specifically. This applies to pretty much any sugar. Here I just happen to choose mannose for the example, right? So 2 hydroxyls to the left, 2 to the right, 6 carbon chain altogether. So for mannose, if you derive, basically go through the Haworth projection and make all your way to the cyclohexane structure, what you usually derive is the following structure. And specifically, position 1 is this one right here. We know that because the oxygen of the ring has to be position 6. And if you move towards, or around the ring rather, if you move around the ring in a clockwise direction, you go from position 6 back to position 1, then 2, 3, 4, and 5. One kind of shortcut that you can apply is to look at this thing and say, well, at position 2, the hydroxyl is to the left, which means that it's going to end up above hydrogen. So positions 2 and 3, the hydroxyl is above hydrogen. And if you look at position 2, the hydroxyl is in fact above hydrogen. Position 3, the hydroxyl is also above its corresponding hydrogen. At position 4, excuse me, you have the hydroxyl to the right, which means that it's going to be below the hydrogen. So you see that position 4, the hydroxyl is in fact below hydrogen. And then the penultimate carbon, which has hydroxyl pointing to the right, means that this is a D sugar, which ultimately means that the CH2OH fragment will be pointing up. Or another way to put it, the CH2OH fragment will be above hydrogen, right? So that's how you should be thinking about your cyclohexane structure. So you might not need to do the full procedure I showed you in the previous videos, but you probably will have to do that procedure at least once or twice to be comfortable enough to do what I just showed you right here. All right, so anyway, the idea right here is that with mannose, um, you have a bunch of alcohols, right? And this is true of the Fischer projection as well. But the carbonyl, right, is now turning into a hemiacetal. Now, if you simply react this with excess alkyl halide, like in this case methyl bromide, in the presence of a mild base, silver oxide specifically, what you're going to end up doing is alkylating every single one of the free alcohols in the sugar pyranose structure. And so ultimately what you'll end up with is the methoxy derivatives in total, right? And even though this is a 6-member ring, remember, one of the oxygens is already been turned into an ether functionality, so you only have 5 to go with, right? So that's why I'm saying 5 equivalents of silver oxide to ultimately turn into silver bromide and silver hydroxide while methylating each of the oxygens. As far as the mechanism is concerned, the alkylation simply follows the typical SN2 route that you might expect. The alcohol comes in contact with your methyl bromide, so the alcohol attacks the methyl, the bromide leaves as a leaving group, and you end up forming your protonated ether moiety along with the bromide anion. Now that mixture is what ultimately reacts with silver oxide. And you got to think of this as an ionic substance, which is exactly what it is. But the interesting thing about this base is that yes, it is a pretty, technically speaking, it's a strong base because oxide is a lot stronger base than hydroxide. But this is an insoluble salt. That said, there's a little bit of an incongruency between silver plus, which in inorganic chemistry we refer to as a soft cation or a soft acid, and oxide, which is what we consider in inorganic chemistry a hard base. In the theory of soft and hard acids and bases, the idea is that soft cations meet with soft anions, and hard anions meet with hard bases. So technically speaking, this is kind of ready to do some chemistry, so it's not as unreactive as you would think due to the insolubility. So the oxide simply attacks your H, the hydrogen goes back to oxygen, turning that oxonium ion into just neutral oxygen. But in the same process, you end up yielding hydroxide, right? So over here now you have silver hydroxide being formed as a byproduct, And the second silver that was part of the original reagent now combines with the bromide that's free floating there to make insoluble silver bromide. So you end up, methylating that position. And then this same exact two-step mechanism happens for the other four hydroxyls in the same exact fashion to ultimately yield the fully methylated product. So that's basically the mechanism, right? I mean, we could do it, like I said here, 8 more times, but I think you get the picture. So that's one reaction. And this is, formation of an ether variant of your sugar. You could do it with any primary alcohol, really. Oh, excuse me, any primary alkyl halide. So, just keep in mind your benzols, your alleles, allyl halides, primary alkyl halides. They will do the trick. All right. So the other thing that we could also do is turn this thing into an ester. And in order to do that, using mannose once again as the example, you have to treat this with an anhydride. That anhydride also has to be treated with tertiary base like pyridine to remove protons. And pretty much what this will do for you is, yes, kick out pyridinium acetate as a byproduct, but more importantly, it will form your pentaacetate derivative, which by all intents and purposes, that is an ester. So the mechanism pretty much follows carbonyl chemistry, right? So first we do a nucleophilic addition onto the anhydride, right? So one of the OHs of your sugar will attack one of the carbonyls of anhydride. It will, push the electrons back to oxygen. It'll give you this switterionic intermediate, which will undergo elimination. So now here what will happen is that the oxide that we have generated will simply use a pair of electrons to reform the double bond, and that act will push out the semi-decent good living group acetate. All right, so this will ultimately generate your protonated ester and one equivalent of acetate. So simply what happens now is that the pyridine that you have lingering around comes around, removes the proton from your protonated ester, attacks that proton, the electrons go back to oxygen, and what that means is that now you have produced an equivalent of pyridinium acetate as a salt byproduct, but you have also acetylated that alcohol position. So you could imagine taking this three-step mechanism, doing it 4 more times. So basically, 12 more steps or 15 steps in total. That will get you to the final acetylated, no, pentaester product. Okay. All right. So one more to show you within this, kind of, thinking, the alkylation and the esterification. Um, we can alkylate exclusively just position one. Um, and the reason for that is because out of all the OHs that we have in this molecule, it's only the OH at position one that is actually a hemiacetal group. So we can actually take advantage of hemiacetal chemistry um, to produce exclusively only the alkylated or ether product just at position one. Another way to put it is that this reaction is reminiscent of taking an hemiacetal all the way to an acetal, derivative. So that's the reason why we have to use acid catalyst to perform this reaction. Because recall from aldehyde and ketone chemistry, if you're trying to make an acetal derivative, you cannot do that under basic conditions. It has to be acid conditions. So here's the mechanism of this. First, you protonate your hemiacetal on the sugar, right? So you get the alcohol at position one to attack your catalytic acids. In the process, you kick off chloride here and you protonate the alcohol. So now you have water as a leaving group. And because of the oxygen, the ether oxygen of that hemiacetal, which itself has lone pairs, basically what happens here is that a lone pair of that oxygen is borrowed to form double bond between that oxygen and carbon 1 of the chain. That in essence allows the water leaving group to take off. And now you have this oxonium I guess oxinium technically, intermediate, which is now got an activated carbonyl carbon to be attacked. So that's where the alcohol kicks in, right? Because now you can have your methanol coming in, attacking the activated carbon of your carbonyl. The electrons go back to the oxonium oxygen to make it neutral, and you end up with your protonated ether derivative along with your chloride, right? So then the last thing is that you use deprotonate that, chloride comes in, removes that proton, and you end up making your acetal, derivative. Now this one technically derives from idose sugar. So I changed the sugar for this example, yes, because I got a little tired of using mannose too much. Um, so as far as the name goes, this is a methyl ether derivative. So you call this methyl D alpha idoside. Alpha because I happen to draw the alpha anomer specifically, but the reality is you're going to get alpha and beta as a mixture. But this specific drawing is the alpha anomer. And then notice that instead of saying idose, I'm dropping the E ending and I'm replacing it with ide. And that tells me that the hemiacetal hydroxyl has been turned into a well, basically a full-on acetal, right? So an ether functionality ultimately. So just keep that in mind because you might need to do that for glucose, right? So glucoside or taloside, etc., etc. Okay, that takes care of the regular alkylations. In the next video, we're going to talk about the reductions and possibly the oxidations as well. So I'll catch you on that video. Bye bye.